Guys, welcome back to another video. Today we're going to be talking about the power series of e to the x squared, okay? And so this is interesting because we know that it's incredibly easy to differentiate e to the x squared because it would just be 2x e to the x squared, right? But it's super hard to integrate because there technically are no elementary function solutions of the integral of e to the x squared. So today we're going to be integrating e to the x squared, but instead of integrating it with the normal way, I guess you could say, by using functions, we're going to use power series, okay? So the first step of that process is, what is the power series of e to the x squared? So to really think about this, we first need to consider what is the power series of e to the x, right? And so we know that the power series of e to the x, I'm going to make this really big for you guys, just so you can see it super well. Let me push the chair out of the way. We know that e to the x is equal to the power series of x to the n over n factorial. Meaning, and this is going to be the infinite series of this from n equals 0 to infinity. And we know that this is going to converge for the interval of convergence for this, rather. Oh my god, that's the worst infinity I think has ever been drawn. Is going to be negative. Oh my, it gets worse. Sorry. It's going to be negative infinity to infinity. Okay? And so now if we write this out, we could say that e to the x is equal to, okay, x to the 0 power, that's 1, over 0 factorial is 1, plus, then we'll have x over 1 factorial plus x squared over 2 factorial, so on, right? Okay? And therefore, we can now say that if we had e to the x times x, we could just plug in x squared to every place we see x. This is just a direct substitution. Okay? And now we can see here, if we plug x times x in here, we're going to have 1. 1's going to stay the same. Now we're going to have x squared over 1 factorial. And this is the factorial symbol, the exclamation point. If you ever see me drawing that and you didn't know, now you know. Then we also are going to have x squared to the second power over 2 factorial. And then we're going to have x squared to the third power over 3 factorial. Okay? And so now if we try to find a general form of this, we could say, okay, we know that we're going to have 1 x squared, x to the 4th, x to the 6th. So wouldn't it make sense if it was just x to the 2n over n factorial? Because we know our factorials on the bottom are not changing, right? It's just, okay, if we have x to the 2 times n, and this is n equals 0, then we know that this would be x to the 2 times 0, which is 1. Then we'd have x to the 2 times 1, which is 2. Then we'd have x to the 2 times 2, which is 4. And we know that this is really x to the 4th because we multiply our exponents when we're raising an exponent to an exponent. So therefore, we can say that this is just x to the 2n over n factorial. And to see where this converges, we can apply ratio test. Limit as n approaches infinity of the absolute value of x to the 2 times n plus 1 over, and then you multiply by, I'm really sorry guys, I'm going a little too fast. Then you multiply this by the reciprocal of this, and we can see here that now this is equal to limit n approaches infinity of absolute value. Make sure you guys can still see that. I'm actually going to move this up here. I'm going to remember, I'm just going to add up here that e to the x squared is equal to the infinite series from n equals 0 to infinity of x to the 2n over n factorial. Okay? So now, seeing with our definition of the ratio test, we remember now that this is limit n approaches infinity of x to the 2n plus 2. This is just what I wrote down there below. N factorial over x to the 2n, n plus 1 factorial. Okay? An absolute value of this. However, all of these are positive, so we actually don't need those. Okay? And so when taking this limit, we can consider, okay, if we have n factorial, we could just rewrite this as n times n minus 1 times n minus 2, so on until infinity, right? And here we could rewrite n plus 1 factorial as n plus 1 times n minus 1, so on and so forth. And so we can realize that these will cancel forever, leaving us with just an n plus 1 on the bottom. So now rewriting our limit, we can see that now we have x to the 2n plus 2. However, we know that these have the same base, and because we're dividing, we can just subtract the powers. So now we're going to have x squared over n plus 1, okay? And that's all we're left with. And that's what's so nice about ratio test when you're dealing with these factorials, is they just cancel out very nicely. Now, because we're taking the limit with respect to n, x is technically a constant, meaning that we could pull it out, saying that we have now x squared, limit as n approaches infinity, of 1 over n plus 1. We all know that as this gets infinitely large, this gets infinitely small, eventually approaching 0. Therefore, we can say that this is x squared times 0, which is equal to 0, which is less than 1, and therefore this converges from negative infinity to infinity. Okay? Beautiful. So, now that we know it's convergent for all terms, now we can take the integral of this, and now it's where it gets interesting, right? So if we take the indefinite integral of the series, so let me rewrite this here. Make sure it's pretty visible for you guys. Of x to the 2n over x to the 2n over n factorial. Okay, so, and this is gonna be in respect to n. Okay, so cool. We know that when we're integrating in respect to n, we're gonna be integrating in respect to x, actually. That's my mistake. And so when we're integrating in respect to x, we see that 1 over n factorial, that's just a constant term, right? And we can pull constant terms out of our integrands. So now we can see that this is now 1 over n factorial, integral of the series from n equals 0 to infinity of just x to the 2n dx. Now we can see that this is simply power rule, okay? And so now erasing this here and this step above and bringing this back up here, we can see that now we're going to add 1 to this power, then divide by that power. So therefore, we can say that this is equal to the power series from n equals 0. Okay, remember x to the 2n plus 1, divide by that. So now we're going to have x to the 2n plus 1 over 2n plus 1 times n factorial. And we might say plus c. It's a convention to put plus c in the front when we're dealing with power series. So we're going to have c plus, and there you go. Integral, and I'll rewrite it up here just so it's nice and neat. Integral of e to the x squared dx is equal to this. And I feel like I find that very, very cool. We can, sometimes when things are too hard to integrate in their base form, we can say, okay, I'm going to stop trying this. I'm going to put it in its power series representation. And we know that this is a perfect representation of e to the x squared from negative infinity to infinity if we have the infinite series of this. So this is essentially e to the x squared. And I just find it so cool that when we're integrating stuff like this, it's so easy. We literally just added 1 to our thing, and then we divided by that thing, and it was incredibly simple. And so yeah, I just think that is it's very interesting. Well, thank you guys.